Relativity. This is a video on the theory of relativity. There are two theories, special relativity and general relativity, and we will explain both. This video explores the physical meaning in depth, with almost no mathematical steps omitted. Relativity involves many complex and lengthy equations, but every step is shown visually, progressing without interruption to the final form. This structure prevents beginners from drowning in the computational and mathematical hell that often causes people to give up on relativity. A distinctive feature of this video is its textbook format, allowing you to review it repeatedly without confusion. The narration follows the on-screen text directly. We recommend pausing at key moments to reflect on the physical meaning and mathematical derivations until you're satisfied. If you've already studied relativity, feel free to jump to any topic of interest. Time and space were believed to flow and exist equally for everyone, absolute and unchanging. According to Einstein's special theory of relativity, published in 1905, time and space are not absolute, but can stretch and contract. Inside a rocket moving at high speed, space contracts and time slows down. 10 years after special relativity, in 1915, Einstein published the general theory of relativity. This is an extended theory that incorporates gravity into special relativity. He discovered that the curvature of space-time is the true nature of gravity. Relativity unveiled the mysteries woven into the geometric patterns hidden in this universe: time and space, light and gravity, immense energy. Today, this once unthinkable theory has become an indispensable foundation of physics for understanding the vast cosmos. Special relativity. Let's first cover a few key points essential for understanding special relativity. In special relativity, the term inertial frame appears frequently. Let's make sure we have a clear understanding of what it means. An inertial frame is a frame of reference that satisfies Newton's first law, the law of inertia, meaning an object at rest remains at rest, and an object in motion continues in uniform straight-line motion unless acted upon by an external force. In simple terms, it is a frame that moves at constant velocity. The term inertial frame may sound complex, but if you think of it as a system where everything moves at constant velocity, it becomes straightforward. One of the most important points in understanding special relativity is to always clearly identify whose perspective we are describing for any given physical phenomenon. Simply being aware of this will prevent a great deal of confusion. In special relativity, we conventionally distinguish between two frames: S, the frame of the stationary observer, and S prime, the frame moving at constant velocity relative to S. What do we mean by relativity? Consider a situation where S prime moves uniformly along the x direction as observed from stationary S. The origin O of S remains at rest for all time. The origin O prime of S prime moves in the positive x direction over time. Now, what does S look like from S prime's perspective? Here lies the key to what we mean by relativity. From S prime's viewpoint, S prime is at rest at its own origin O prime. Meanwhile, S recedes in the negative x direction at constant velocity. This may be hard to visualize, so let's try a thought experiment. While you're fast asleep, someone moves you onto a vehicle in uniform motion. You wake up and realize you're in a different space, but you're aware that you're stationary in this location. You glance out the window and see the outside scenery moving at the same speed in the same direction. You remain seated without moving. You'll surely think, I am stationary and the scenery outside is moving. Then you see S, the stationary frame we initially defined. S, which was far away at first, approaches closer and closer, eventually disappearing from view. From S prime's perspective, S prime itself is the stationary frame, and S is the one moving. Thus, observers in uniform motion cannot distinguish whether they are stationary or moving at constant velocity. Right now, you are stationary in front of your screen, but in fact, Earth and the solar system are also moving, not necessarily at constant velocity, but moving nonetheless. Earth rotates at about 1,670 kilometers per hour and orbits the Sun at 107,000 kilometers per hour. The solar system itself moves through the galaxy at 828,000 kilometers per hour, yet you feel none of this motion. Returning to our discussion, from S's perspective, S is stationary and Sprime moves at constant velocity. From Sprime's perspective, Sprime is stationary and S moves at constant velocity. This is what we call relativity. Thinking this way, we can say there is no absolutely stationary frame in this universe. Before Einstein's special relativity, time and space were considered absolute. This is called absolute time and absolute space. Even today, our daily lives are built upon this as common sense. The idea that time and space could differ from person to person is unthinkable. If that were true, what foundation would our daily lives rest upon? Let's trace how Einstein came to reject this seemingly obvious notion of absolute time and absolute space that no one had questioned. Galilean transformation. We derive the Galilean transformation, the coordinate transformation used before Einstein. Setup. Consider two inertial frames, a stationary frame S and a frame S prime moving at constant velocity v in the x direction relative to S. We set y equals z equals 0. Since time is absolute, t equals t prime. At the moment when O, the origin of S, where x equals 0, and O prime, the origin of S prime, where x prime equals 0, coincide, both observers start their stopwatches simultaneously. After t equals t prime seconds have elapsed, we determine x prime, the position of the object as measured from O prime in the S prime frame, using the values measured by the stationary frame S. We are finding the x prime coordinate in frame S prime using the measurements x and t from frame S. From S's perspective, after t seconds, x prime has moved a distance vt in the x direction as measured by S. This vt represents the distance traveled by the origin O prime of S prime as observed from S. Let's verify the units. V in meters per second multiplied by t in seconds gives us meters, a unit of distance. Therefore, x prime as measured by S is x prime equals x minus vt. Combined with absolute time, this is called the Galilean transformation. To avoid confusion later, let's clarify how to interpret coordinate transformation equations in relativity. The left-hand side represents what S prime measures in its own frame. The right-hand side expresses the same quantity using S's measurements. The equation connects observations from two inertial frames. We now rearrange the Galilean transformation to solve for x equals x prime plus vt. Since the two inertial frames are connected by an equation, this expresses x in the S frame using S prime coordinates. This is called the inverse Galilean transformation. Velocity addition rule. Using the Galilean transformation and its inverse, let's examine how velocities add or subtract. Setup. A train moves at velocity v along the x-axis relative to s. At t equals 0, when O and O' coincided, a ball was launched from O' in S' frame. At time t, the ball is observed at position x in the S frame and at position x' in the S' frame. Let u be the ball's velocity as measured in the S frame, and u' be that in the S' frame. The distance traveled by the ball in the S frame is x of t. Therefore, the velocity u of the ball is the distance traveled by the ball in the S' frame is x', t'. Therefore, the velocity u' of the ball is. This section shows the derivation. Feel free to pause and follow the equations at your own pace. Now that we have derived the velocity equations for a moving object in both the stationary frame S and the moving frame S', let's consider a specific example. A car is moving in the positive x direction at a constant velocity of v equals 60 kilometers per hour, as observed from the stationary frame S. A ball is launched from the car in the same direction at a velocity of u' equals 100 kilometers per hour. The velocity of the ball as measured in frame S is u equals 100 plus 60, which gives us 160 kilometers per hour. Next, we find the velocity of the ball as measured in the S' frame. Substituting the ball's velocity observed in the S frame, u equals 160 km per hour, and the car's velocity v equals 60 km per hour, u' equals 160 minus 60 equals 100 km per hour. Now let's analyze these results. In the S frame, 160 km per hour. In the S' frame, 100 km per hour. The ball's velocity differs between the two frames. This is actually quite natural. Since the S' frame moves together with the car, the observer is always at the origin O'. X' equals 0. From this origin, the ball travels 100 kilometers in 1 hour. Now comparing the two frames. In the S' frame, the ball travels 100 kilometers in 1 hour. The car itself moves 60 kilometers in that same hour. So in the S frame, the ball is at 100 plus 60 equals 160 kilometers. Since velocity equals distance divided by time, where t equals t' here, the ball's velocity, as observed in the S frame, is naturally measured as greater than in the S' frame. In everyday life, this velocity addition rule holds, and it is confirmed by experiment. But what happens when the ball is replaced by light? Let's consider whether the velocity addition rule applies to the speed of light. Velocity is calculated as distance divided by time. That much is certain. For simplicity, we consider a rocket moving in the positive x direction, emitting light in the same direction. Suppose that from a stationary frame S, a rocket, the S' frame, moving at half the speed of light emits a beam of light. Let's substitute our assumptions into the velocity addition formula. The speed of light observed in the S' frame is c, so u' equals c. The rocket's velocity is 1/2 c, so v equals 1/2 c. U equals c plus 1/2 c equals 3/2 c. The speed of light has been exceeded. In terms of distance, from c equals x over t, we get x equals ct, and from 1/2 c equals x over t, we get x equals 1/2 ct. adding these. X equals ct plus 1/2 ct equals 3/2 ct. Now what about the speed of light in the S prime frame? In the S frame, we have u equals 3/2 c and v equals 1/2 c, so u prime equals 3/2 c minus 1/2 c equals c. Since observations in the S prime frame are always made from the origin O prime, this is a natural result. The distance light travels is given by c equals x prime over t prime, so x prime equals ct prime. We are dividing different distances by the same time t equals t prime, so naturally the speed of light appears to change in this way. Physicists at the time, in the late 19th century, naturally thought the same way. They believed that light was a type of wave that propagated through a medium called the ether, that an absolute coordinate system at rest relative to the ether, an absolute rest frame, existed, and that if the light source or observer were moving, Galileo's velocity addition rule would apply directly. In other words, that speed of light plus observer's velocity equals observed speed of light should hold. However, the Michelson-Morley experiment of 1887 demonstrated that the speed of light remained constant regardless of the direction of Earth's motion, the velocity of the light source, and this became a profound mystery. Physicists such as Lorentz and Poincaré took on this challenge, but none could break free from the framework of the ether. The decisive difference with Einstein was this. Whereas other physicists attempted to patch up the problem while keeping the ether, Einstein made a radical shift in thinking. Neither the ether nor an absolute rest frame is necessary. The speed of light is constant for all observers. Let us take this as our founding principle. That the speed of light is constant means c equals x over t equals x prime over t prime. In other words, he abandoned the common sense notions of absolute time and absolute space. This is the revolutionary nature of the special theory of relativity.